Welcome back. We are in lecture 5B of Fundamental of Electronics. We were discussing the bipolar junction transistor. This is the second part of the discussion of the BJTs. So we will discuss the bipolar junction transistor. The first, what are the connections overview of the different types of BJTs. So three important configurations are there in which the BJTs are usually operated or it is taken into application. The first one is basically the common emitter mode. So we write as CE as the short form. Then we have the common collector mode, CC, the common base form, that is we have the CB. Mostly we are using the common emitter configuration, and hence we will focus this chapter to discuss the operation of BJT in the common emitter configuration. So the common emitter circuit, if we see, so here we have the NPN transistor where the emitter is basically grounded. So emitter, we can see here it is ground, and the emitter is basically common to the base and the collector. So we have basically two important loops. One is basically the base loop. So this is what we have, the base loop, and another one we have the collector loop. So here we have the collector loop. Base loop is forward biased. So since the transistor is NPN type, so N type will be connected to the positive terminal of the supply, and hence we can say that the base emitter junction is basically forward biased. On the other hand, if we see the collector emitter junction, that is basically reverse biased, because the N type material is connected to the positive terminal of the supply. So we have the supply in the base, which is denoted by VBB, and the supply which is connected to the collector is denoted by VCC. There are two resistors, RB and RC, in the base and the collector region, which will be limiting the current, and the emitter is basically grounded. So the potential that we get at the base is basically VB, and the potential what we get at the collector region is equal to VC. So the basic key insight is the base current will control the collector current. Now, what is the voltage behavior in this type of circuit in the common emitter configuration, where the base current is generating the voltage across the RB? So you have the resistor RB and there is a source which is connected, VBB. So there will be a current which is the base current, and this base current will be flowing through the base region of the transistor, and the polarity of the potential across the RB in accordance with passive sign convention is basically shown here. The collector current creates a voltage across the resistor of the collector. So you have the collector supply and there is a resistor RC. So the collector current which is flowing from the source will have the potential drop. So here, in accordance with passive sign convention, we have the potential drop across the RC region. So collector must remain positive for the proper operation. So you need to have a proper operation in the common emitter mode, and hence we have to keep the collector under positive zone. Now, what is the meaning of double subscript notation? So this point has to be noted that when we are writing the voltage source as in same subscript VBB and the double mode, then that indicates the source voltage. Whereas when we have the different subscript, that is example we have VBE or VCE, then you have the 2 points. So it is basically the potential difference, and the positive meter probe will be on the first subcircuit. So if you have like VBE, then you have basically this is positive and this is negative, and the common probe will be in the second subscript. Then these potential VBE can be further taken as the subtraction or the difference between the base voltage and the emitter voltage. So the examples that we take for double subscript, whether it is VCE, VCB or VBE, can be written as the difference of the voltages with the first notation what we have VC, that will be given as positive polarity, another will be common. So we have VC minus VE representing the voltage of VCE. Similarly, VC minus VB and VB minus VE will be the voltage which will be represented by VCB and VBE. So this circuit in the common emitter configuration, if we see it, since the emitter is basically ground, so we have here 0 volt. Now if we talk about the VCE voltage, so if you see here what is the potential of collector to emitter. Now the emitter is usually at 0 volt because it is grounded, so the potential of this point will be directly as plus VC. Now note here, this is single subscript, whereas the source is given by double subscript. So we have VCC, which is the source, but here we have plus VC, which is at higher potential compared to the ground. Similarly, if we are talking about the potential of base to emitter, then the emitter is basically at 0 volt. So the base voltage what you have is basically positive, which is given by plus V. Similarly, the source here is basically represented by the double subscript, which is given by VBB. So there is a difference in which the sources are basically represented and the potential drop meters which is connected between the 2 points. So when we talk about the single subscript notation, we have to be careful that usually the VBB and VCC are the sources, and the voltage what you have at the base and the collector will be with respect to the common point. So the common point, which is the emitter, is at 0 volt. So this will help to calculate the potential in different points in a better way. When we talk about the base curve, so base curve is basically the curve which is obtained between the base voltage, which is IB, and the potential VBE, base to emitter, and this resembles a diode curve. So diode we have discussed in very detail, where there is a voltage, threshold voltage of 0.7 or 0.3 depending upon what transistor, what diode we are using, whether it is silicon or germanium. After that you have a sudden rise of the curve. So if you increase the base to emitter voltage, then the base current will increase. So here the emitter diode is basically forward biased. So here you have the emitter which is grounded 0 volt, and the base current will flow in the base region, and you have the collector current which is flowing in the collector region. So the base current can be written in the KVL equation form and the KCL equation form. So here what we have, the difference of the potential VV minus the base emitter. So here you have the potential base emitter VBE, but since the emitter is grounded, so this will be directly can be written as VB. So you have the difference of the potential in the numerator, and in the denominator you have basically the RB, which is the resistance of the base. So this is in accordance with the Ohm's law, and the KCL equation you can apply at this node where all the currents will be meeting. Then the approximation that we take for the base emitter, if we are taking the ideal diode, then the base emitter will be 0 because then we think that there is no threshold voltage. So without applying the base emitter, we are getting the base current. But the second approximation, we should take the base emitter as sudden drop, which is for the threshold value, and this will best balance between the speed and accuracy. When we talk about the collector curve, so collector curve is drawn between the collector current and the potential what you have is the collector emitter voltage. So you need to fix the base current first. So whatever the base current is flowing here has to be fixed. So these can be fixed only when the source is fixed, that is VB, and you can vary the collector voltage VCC, and you measure the current IC and VCE. Now if you observe this waveform, collector emitter voltage will be 0, then there will be no collector current. So this is the point which we are talking, where the collector emitter voltage is basically 0 volt. So you do not have any current in the collector. So collector current is also 0. Now if you increase this voltage, collector emitter voltage, then you will be seeing that the collector current is rising sharply. So there is a sharply rise of the current, and then it is stabilizing to a fixed magnitude of the current. We have taken one example here for 10 microampere. So they depend upon what is the value of the source. So this is just an example. So we can see here the base collector current is constant, and after that, when the collector emitter voltage of certain higher limit is crossed, then we have the sudden increase of the collector current. So beyond this potential of collector emitter, the transistor will break down and it will stop working. So the significance is collector current, if we are talking about, it depends upon the emitter junction and not the collector emitter potential. So whatever the current is flowing in the collector IC, this is directly dependent on the emitter junction. We do not depend upon the collector to emitter voltage. Now when we talk about the voltage and the power in calculation in the circuit, then we use the KVL equation. So what is the KVL equation you have? So there is a potential VCC, and there will be drop here, which is the collector current, and multiplied with the resistor of the collector. So you will be getting the potential collected to emitter. So this we can write the KVL equation. Collector to emitter is nothing but the voltage drop from the collector region due to the resistor RC. And the power dissipation that you have is basically the product of the voltage, that is VCE, and the collector current IC. So critical point, if we talk about, then the power raises the junction temperature. So if you have the voltage drop as more, then you will have more power rises, and this will burn out at a certain temperature of 150 to 200 degrees centigrade. So you should ensure that the working power PD should be less than the maximum power PD max. So here if we cross this 40 volt limit for an example, then you are in the breakdown region and the transistor will burn out. So the region of operation, if we see, there are three important regions. We have the active region, the saturation region, and the breakdown region. Now what is the active region? So active region is the region where you have the collected to emitter voltage varying from 1 volt to any higher limit, which is specified in the nameplate detail of the transistor. Here an example we have taken as 40 volt. So here this region is basically known as the active region. So in the active region, what will happen? The collector current will be constant. So if you see here, the collector current is constant, and it is independent of the change in the voltage of VCE. So whatever the VCE you are changing, it doesn't change the collector current. Emitter is forward biased and collector is reverse biased. So your base emitter junction, this will be forward biased, and the collector emitter junction will be reverse biased. When we talk about the saturation region, so saturation region, if we see here, this is a very small region here. So here the collector emitter voltage is less than 1 volt, and there will be insufficient voltage to collect all the free collector currents, and hence in this region the current again beta, which is basically the collector current by the base current. We have already discussed this in the previous lecture. So if you see, the collector current is less but the beta current is quite high, so your beta is low. Now talking about the breakdown region, so this is the breakdown region. In the breakdown region, the collector emitter is greater than the higher upper limit, which is specified by the transistor, which is in this case 40 volt, and the transistor will be destroyed, and you should avoid the operation in this region. So breakdown region, no operation should be there. It is the region which is mentioned so that all operations should be below the breakdown region. Now what are the key takeaways for this discussion is that we should take the second diode approximation always for the calculation. It means that you should take the base emitter drop 0.7 volt or 0.3 volt depending upon whether you are using silicon or germanium transistors. Now, you should maintain the power drop and the collector emitter within the safe limit to avoid any burnout. And you should understand the active region, saturation region, and the breakdown region for the proper transistor operation. Now, taking forward, let us go to the collector curve now. So, if we observe that the collector current and collector emitter, if we take one example where the base current is constant, that is 20 microampere. So here you have the base current 20 microampere, and in this region if you see the collector current is constant, so you do not have any change in the collector current, and all this current whatever we are getting in the collector curve is basically you are changing the base current. So base current has to be constant. So collector current will be equal to beta DC into IB, because beta is nothing but the ratio of collector current by base current. So for all this curve, if you obtain the beta, that will be constant for a particular case. Hence, beta is constant for all curves in the active region. So here you have the active region where the beta is constant for each curve, and you need to use the curve tracer to display this collector current versus collector to emitter voltage. Now, if we revise the transistor operating region, in the active region, you have basically the linear region. This is where the amplification is possible and input signal will produce the proportional output. The collector emitter voltage will lie between the lower limit, which is in this case 1 volt, and the higher limit, which is equal to 40 volt. The collector current is given by the product of beta into IB. Beta is constant in this case for the active region. When we talk about the cutoff region, the base current is 0. Collector current, due to collector cutoff current, you will have a reverse minority carrier current. So this we have discussed what are the reverse minority carriers in the hole and the electron type. You can see that in the diode discussion. So there will be surface leakage current when we have the cutoff region. So collector current in the cutoff region, you see this value is very less in nanoampere, 50 nanoampere for a particular case of the diode or a transistor given by 2N3904. So here you have the negligible impact in well-designed circuit. So the collector current do not change here in the cutoff region. Saturation region, where you have the collector emitter voltage less than 1 volt, base current is dominating and the low current gain you get it. The breakdown region, where the potential is greater than the higher limit 40 volt and the transistor will destroy due to excessive current. So the application of these operative zone, when you have the active region, you will be having the signal amplification, and the change in the base current will result in a proportional change in the collector current. So you have the linear region operation and you have the signal amplification. When you talk about the saturation and the cutoff region, both these regions are basically for the switching circuit which are used for digital and computer systems. In the saturation, it behaves as closed switch, and the cutoff region, it behaves as open switch. So whether your switch is open or closed, that is given by the saturation and the cutoff region. So transistor will act as a switch in the saturation and cutoff region, and transistor will act as a power amplification source in the active region. Breakdown region, you should avoid it because this will lead to irreversible damage for the transistor. So the key observation that we have for transistor curve is basically the curve shape remain consistent across the transistor types through beta DC, which is may vary for a particular case. Amplification occur only in the active region, and small collector cutoff current is generally negligible. So we do not take this cutoff current into account. Saturation and cutoff region are essential for digital logic circuits because here what you have the switching operation. So when we recap and do the insight for the transistor, we have basically the four region of operation: active, saturation, cutoff, and breakdown. Amplification is possible only in the active region because of the linearity. The saturation and cutoff region are critical due to in the digital switching network, and always consider the design limit that is provided in the data sheet, whether collector emitter voltage, the beta value, that is the current gain, and what is the saturation current cutoff. Now, the transistor equivalent circuit, if we talk about, we have seen that there will be two region, base emitter region and collector emitter region. Both will have its own voltage, and the transistor will be modeled as a diode in the base emitter junction. So when we talk about the base emitter junction, this will be represented by a diode, and the current source will be represented at the collector side. So this is the collector side, which will be represented by current source, and the collector current is given by beta into IB. So this we can see in the circuit where you have the diode here in the base emitter junction and the current source which is given by beta into IB in the collector region. Now if we do the ideal approximation, what is the meaning? The ideal diode we are using where the base emitter is basically 0 volt we are taking, and the base current is then given by the voltage of the base divided by the resistor, whereas the collector current is given by beta into IB. This is useful for troubleshooting and quick rough approximation, but generally we go for the second approximation where the base emitter potential we take as 0.7 volt for silicon transistor, 0.3 volt for transistor in germanium, and here these account for the voltage drop in the emitter diode. So generally this calculation of IB, you have an extra term which we are taking out the base emitter, which is 0.7 volt or 0.3 volt from the source VBEB in the calculation of the base current. The collector current is given by beta DC into IB, which is same as the previous case, and this is common in low voltage circuit to improve the accuracy over the ideal approximation. If we go for the higher order approximation, we have to include the bulk resistance effect. This we have discussed in very detail in the diode discussion, what are bulk resistance. So you have the resistance of the p-type and n-type material. So that resistance also you will be having certain drop. So high current when the transistor is flowing, emitter diode resistance increases the base emitter voltage. So base emitter voltage is greater than 0.7 volt, up to it can be 1 volt. Collector bulk resistance may also affect the collector emitter voltage and the collector current. So these bulk resistance effect are accounted in higher order approximation. Other higher order, if we are taking account, then you have the leakage current. There are certain early effects and there is temperature dependence of the parameter. So the recommendation is that use the computer simulation for calculation beyond the second approximation when the complexities are involved. But we go with the second order approximation only. So if we compare this approximation, you have the ideal approximation, second order approximation, and the higher order approximation. In the ideal approximation, the base emitter you take 0 volt, their accuracy is low and it is generally used for troubleshooting or rough calculation. When we go for the second order approximation, the base emitter voltage we take the drop 0.7 volt for the silicon transistor. Here the accuracy is moderate, but it is most general purpose circuit. Higher order approximation, we include the bulk resistance, early effect, and other complex phenomena, generally for high power or precision applications. So the key takeaway that we have from this discussion is the approximation trade-off: accuracy for simplicity. So use ideal for quick estimate and then go for second for better accuracy, usually in the low power circuit. Rely on the higher order approximation or simulations when you want to do the calculation for high power and the precision designs. Emitter voltage, base emitter voltage, usually for second approximation we have to take 0.7 volt, which is typical, but it increase with current in high power circuit. So these 0.7 volt generally we take as second order approximation, which we include mostly for the calculation. Bulk resistance and other effect we can think to be negligible in most low power circuit and hence significant only in the high power design. So here we have discussed in lecture 5b the circuit in the color in the three configurations. We will discuss other two configurations in detail in the coming lectures. But we have seen the base curve, collector curve, and all the equations relating the KVL and the KCL, and how these region of operations in active, in saturation, and cutoff are there. So, which is very important for the BJT operation. Thank you for now. See you in the next lecture.